Have you ever needed to yell out to someone far away in a crowd without causing a scene? You could use a megaphone to be loud enough, but while effective, it's hardly subtle and pretty much guaranteed that everyone in that crowd would hear you. After all, basic intuition is that sound should spread out in all directions from a source, reflecting and diffracting until it fills the space. But what if you could build a device that defies that intuition? It turns out that with simple electronics, it's actually possible to easily modulate sound onto an ultrasonic carrier wave, and this allows us to trick the air into delivering the audio only to a specific region in space. Today, I'm showing you how to build a device that does just that, breaking common understanding of how sound should work and allowing you to shoot sound as if it has both the directional precision and intensity of a laser. But before we get into the specifics of this device, how about we go over the principles of acoustic transmission in air that make using ultrasound so much different from audible frequencies. Now, the fundamental idea here is that directivity of a sound source is determined by how large that source is compared to the wavelength of sound it produces. If a speaker is small relative to the wavelength, which happens to be the case for almost all handheld devices playing audible sound, the waves diffract around the edges and spread out omnidirectionally. This means that to get a tight laser-like beam with normal audio, you would physically require a speaker face about the size of a billboard. And since I wanted this device to be handheld, I couldn't change the size of the source, but the easy workaround for this is to change the size of the wave. By jumping up to 40 kilohertz, our wavelength drops to just 8 millimeters. That means that a small, centimeter-sized emitter is now acoustically huge, a whole wavelength across, making high directivity transmission physically possible with just a single bottle cap-sized source. But we don't want just high directivity, we want super high directivity. And the only way to turn this general tendency for sound projection in the forward direction into a collimated beam is to mess around with another concept in wave mechanics, which is interference. By arranging multiple emitters into a parametric array, the parameter here being the spacing between emitters, and driving them all in phase, meaning they all push and pull the air in tandem with each other, we create a unified wavefront that is just about as powerful as the sum of its parts. This is called constructive interference. It's important to note that for an array that is in phase, this complementary action is strongest directly in front of the device, with the waves from every single transducer arriving at the same time and amplitude stacking perfectly on top of each other. But the real trick is what happens off to the sides. As long as that spacing parameter is set just right to 1/2 plus any integer times the wavelength that you're using, you'll get destructive interference that cancels out sound almost entirely off to the sides. Pretty cool, right? But even with a perfect beam, there's still an obvious problem. You can't hear 40 kilohertz. It's way above the audible frequency range for humans. So to make this actually useful, we have to rely on a property of air known as acoustic nonlinearity. Essentially, sound travels just slightly faster in high pressure air than in low pressure air. This means that when we pump out ultrasound at high enough amplitudes, the waves generated actually distort their own shape as they travel. And if we modulate our speech or even music onto that carrier wave correctly, that distortion forces the air itself to demodulate the signal, creating audible sound in midair. The effect of this is like having an invisible speaker positioned right in front of your target, making it seem to an observer almost as if the sound is being generated inside their head. It's a pretty surreal thing to experience. So now that we understand the working principles of this device's output, let's break it open to see how it works. At the very heart of this device, we have a 555 timer circuit, which is operating as an astable oscillator here, generating the 40 kilohertz square wave signal that will eventually drive our piezo transducers. To modulate or interrupt this carrier wave with the audible frequencies that we want to transmit, I simply wired one of the outputs of this Bluetooth audio amplifier into the trigger pin of the 555 timer. That way, when the audio signal is high enough to trigger, the square wave is altered for the relatively long duration of those peaks. Now, I've got to be honest, this is far from an optimized circuit, but as long as I carefully adjust the amplitude of that audio signal with this knob on the amplifier just right, it works decently well as a first iteration prototype, as you'll see later. I also ran into some grounding issues when building this in a rush many years ago. So while the audio amplifier is powered by just a 9 volt, the 555 timer circuit is actually separately powered by the 5 volt output of an H-bridge module that I picked up for just a few bucks. The modulated 40 kHz output of the 555 timer then feeds directly into the control pins of this same H-bridge. And what this does is basically amplify the low power 5 volt output of the 555 into a high power variable amplitude signal that will be capable of driving the whole array of transducers. I've allowed myself to adjust this output amplitude, basically how loud the device will be, just by turning the knob on the back panel, which by changing the resistance of a connected potentiometer raises or lowers the output voltage of a small boost converter that I have sitting right in between the H-bridge inputs and my main power source, a 12-volt nickel metal hydride battery. Then finally, we have the parametric array at the end of all that important circuitry. All 73 of these 8mm diameter piezoelectric transducers have been meticulously wire wrapped and soldered in parallel, with connections at the center that run back to be driven by those H-bridge outputs, as well as a toggle switch in series with this connection that allows me to turn the device on and off. For those interested, here's what the entire circuit diagram looks like. Now that's enough time for explanation. Let's go test it out to see how well it actually works. Now here's another cool thing this device can do. See this microphone and see that wall? It's no surprise at this point that when I stick the microphone in the direct path of the ultrasound beam, that the mic will pick up some music. But watch closely at what happens here. That's right. Because of the coherence of this beam, or the overlapping nature of the waves emitted, I can actually specularly reflect both the ultrasound and the demodulated audible sound it's carrying off of flat surfaces, just like reflecting a laser off a mirror. And since I've got to promote our product, watch the sound perfectly reflect off of one of our 32-inch diameter Lichtenberg figures. Let us know if you want one of these in the comments, by the way. Now these specular reflections are really cool, but there's one problem they actually create. When shooting the beam of sound indoors, the sound will tend to scatter dozens of times off walls and surfaces, diminishing the effect that we were originally going for here. To avoid this issue and truly give an idea of the scales over which this device can operate, let's go outside and see how well directional audio is picked up from over 100 meters or 300 feet away. Now, if you think this device is pretty cool and want to see an improved version in the future, just leave a comment and I'll use this to gauge people's interest and eventually get around to it. This is far from the only device like this out there, so if you have any interest in seeing what other people have done, I put a few links to great videos with similar designs in the description. I hope this video was somewhat informative on the mechanics and operational principles of parametric arrays, but if you're an expert on these devices and saw something wrong that I said, I would be more than happy to hear where my explanation could use some adjustment. Thank you guys so much for watching, and we look forward to seeing you in the next video.